On November 11th of 2022 at the NHRA Finals in California, Brittany Force set the fastest speed in the Top Fuel racing category ever. In only 3.5 seconds, she went from 0 to 338 miles an hour. Top Fuel dragsters are the fastest accelerating vehicles on the planet. They're so fast that they go from 0 to 60 before they even travel their own length, pulling over 8 Gs of acceleration. That is stupid speed that makes Formula 1 cars look like a Ford Pinto, and the engineering behind these 11,000 horsepower monsters is nothing short of incredible. 330 miles an hour in less than 1,000 feet. That's 3 football fields. Just one of these 500 cubic inch or 8.2 liter V8 engines makes more power than the first 5 rows of the Daytona 500 or half of the Formula 1 grid. They drink over 11 gallons of nitromethane fuel per second, more than a Boeing 747 at takeoff. And halfway through each run, the spark plugs get so hot that the electrodes burn away entirely. And after this point, the engine continues to run effectively as a diesel due to the compression and the heat of the exhaust valves, which are now at over 1400 degrees Fahrenheit. The superchargers are so powerful and move so much air that they need 800 horsepower just to turn. This means if you took a stock V8 Hemi and threw this supercharger on top of it, you wouldn't even be able to run it. But all of that power comes at a cost. Top Fuel engines only turn about 540 revolutions from light to light at 9,500 RPM, which means that including the burnout, the engine only needs to be able to survive about 900 revolutions under load. Which sounds unbelievable, but you need to remember that they only run under load for at most 4 or 5 seconds, burnout included. I once made a video about why the V10s in Formula 1 were only able to last 200 miles before needing to be completely rebuilt or replaced. But these engines are pushed beyond the limits of what seems mechanically possible, and need to be torn down, inspected, and rebuilt after every single run as a result. That's if you're lucky and the engine doesn't explode halfway down the track. This is what makes Top Fuel so cool. Not only are they the fastest and the loudest vehicles on the planet, they're also some of the most dangerous, and you never know what's going to happen when the lights go out. But how is it possible to make this much power? And why do the engines have such short lifespans? Well, those two questions kind of go hand in hand. To understand why, we first need to get a grasp of their basic operations and some of the incredible forces that are at play here. If we look at a Honda Accord, it has an engine that can run for hundreds of thousands of miles before it'll bite the bullet. Diesel engines can last even longer than that, and this is because they're designed from the beginning to be smooth, efficient, and reliable for the long haul. Even if we look at hypercars like the Bugatti Chiron, a car that puts out 1,500 horsepower and can do it reliably for tens of thousands of miles, it's easy to forget what can happen when you really push the limits of what internal combustion engines are capable of. But like I already said, when a Top Fuel dragster launches off the line, it experiences forces upwards of 8 Gs, more than what astronauts face during a rocket launch. And this immense force is mirrored internally, with each component under extreme stress. These cars also have no gearboxes. They only have one really big clutch that's connected directly to the drive axle. And this clutch doesn't completely close and lock up until the car is at nearly 280 miles per hour, and only then is the engine able to send its full power to the wheels. And this engine is built off of a basic design that dates back to the 1950s. The pistons, connecting rods, and crankshafts are subjected to explosive combustion pressures and extreme temperatures that can exceed 7,000 degrees Fahrenheit. It's a brutal environment. Now, the secret to the incredible power of these engines obviously lies within its engineering. A combination of massive superchargers, precise fuel injection, and highly refined nitromethane fuel contribute to the explosive power output. But this fuel is where it all starts, and it's basically unlike any other racing fuel, period. As a matter of fact, nitromethane fuel usually isn't used as fuel for engines at all. Instead, it's often used in the chemical industry as a powerful solvent for things like textiles, dyes, pharmaceuticals, and explosives. It's known as a monofuel, which means that unlike gasoline, nitromethane fuel actually carries its own oxygen with it. This is different from gasoline, which needs to be precisely mixed with air to be able to combust reliably. What this means is that despite nitro fuel having less energy than gasoline, it requires significantly less oxygen to burn effectively. Nitro fuel requires just 1.7 kilograms of air to burn 1 kilogram of fuel, whereas gasoline requires over 14 kilograms of air to burn 1 kilogram of fuel. This is because, like we said, nitro carries its own oxygen with it. This means that an engine that's running off nitro fuel can easily make almost 10 times the power of an equivalent engine running on regular gasoline, because you're able to pump almost 10 times the amount of fuel into the combustion chamber than you would be able to if you were using gasoline. But because nitro is such a slow burning fuel, some of it inevitably ends up exiting the exhaust unburned. And this is what causes those insane rooster tails and those big yellow flames as a dragster is launching off the line. It's all of that unburnt nitro fuel mixing with the atmosphere, as well as the hot exhaust temperatures igniting as it leaves the exhaust. With all of this fuel that they burn and all of this power that they're able to generate, you would think that a Top Fuel engine would be some incredibly expensive and complex machine similar to what you see in Formula One. When in reality, Top Fuel engines are actually relatively pretty simple. Their size is limited to 500 cubic inches or 8.2 liters, and they have a simple push rod operated 2-valve head. Very different to the small, complex, and high revving engines used in series like Formula One with complex computer controls and pneumatic valves. This simple design seems almost archaic by today's standards, but this design is set by the NHRA rules and helps significantly with keeping costs down, which is important when you go through engines as quickly as these teams do. They're made out of one solid piece of aluminum, and they don't have any cooling whatsoever. Partly because they run for such a short time, but also because the fuel itself acts as a coolant for the valves and the pistons. The crankshaft is made out of solid billet steel, and the connecting rods are made out of giant hunks of forged aluminum. You might ask, why not titanium? Well, it's because aluminum is a lot better at absorbing shocks and blows than titanium is, which takes a lot of that pressure away from the bearings as well as the block itself. The pressure inside of the combustion chamber is so high, over 13,000 psi, that it actually shortens the length of the connecting rod over the course of a couple of runs. This decreases the compression ratio of the engine and thus decreases the amount of power that they're able to generate. Now, the lifespan of a connecting rod in a Top Fuel engine is typically 10 to 12 runs, but the bearings that connect them to the crankshaft need to be changed out after every single run. And so much heat is being generated during one of these runs that the exhaust valves in the engines themselves need to be made out of a special alloy called Inconel, which is the same material used in the thrust chambers of Saturn V rockets. Now, remember when I said at the beginning that a dragster uses more fuel at a launch than a Boeing 747 does during takeoff? Now that's true, but how do you pump that much fuel into an engine, and how do you burn it all? Well, the fuel is being pumped in at 500 psi with 34 different injectors, 16 in the heads, 8 in the intake manifold, and 10 in the blower hat. And they do this using a 2.5-inch fuel line. It's a fuel pipe. It's bigger than the coolant hoses on my car. They pump in over 100 gallons or 380 liters of fuel per minute at full throttle. That's 5 gallons or 20 liters per second of fuel. These are rates that would flood any other engine, and they result in an explosion that's more akin to a rocket than a traditional car engine. And to burn this much fuel requires some serious power. To be able to ignite that much fuel, they're delivering one 60,000 volt, 1.2 amp spark to each of the 2 spark plugs in the combustion chamber, delivered by twin MSD magnetos. So much power that you could use those magnetos as arc welders. Now, the supercharger that's used to help force all of that air and fuel into the combustion chamber was originally designed to be used on big diesel truck engines. It pumps in air at 65 psi using a huge Kevlar lined belt, and they also have to be covered with a Kevlar blanket because blower explosions aren't exactly uncommon. And all of this air and fuel creates so much energy that just the exhaust itself, which is pointed out and up from each cylinder, adds nearly 1,000 pounds of downforce at launch, which is part of why they're able to get so much traction off the line, because that exhaust is helping force those big squishy Goodyear tires to the ground, but the tires are another video on their own. So why do these engines only last a few seconds? The intense heat, pressure, and force exerted on every component in the engine means that wear and damage occur at a greatly accelerated rate. Pistons crack and melt, connecting rods bend and compress, bearings are prone to disintegration, spark plug electrodes burn away entirely, belts break, blower motors explode, so much fuel is being added into the engine that the engines can actually hydro-lock if the fuel doesn't ignite properly, the crankshafts can twist and distort. In essence, the engine is trying to destroy itself from the moment it's turned on. We also have some more consumable items like clutches, tires, carbon brakes, which need to all be replaced after every single run. Maintaining a Top Fuel dragster is a race against time, and it's not uncommon for teams to only have minutes to rebuild an engine entirely in between runs. If a car makes it to the finals every single race, the engine will be completely torn down, inspected, and rebuilt 184 times over the course of a season. Now, this Herculean effort requires a team of highly skilled mechanics working in perfect harmony. Not to mention the financial cost of running a Top Fuel dragster, while cheap by some other racing standards, is still astronomical. Each run can cost tens of thousands of dollars, with engine rebuilds being a significant portion of a team's budget. New materials and engineering techniques promise to make engines more durable, perhaps extending their lifespan beyond the current limits. That being said, overall lifespan isn't the name of the game here, and if I had to guess, most of the innovation probably goes towards safety rather than reliability. But as reliability increases, so too will the power that the teams push to create until they're just reliable enough to finish the run. But one thing remains certain: The quest for speed will continue to push machines and the people who build them to the very edge of possibility. These engines may only last for 3 seconds, but the legacy that they leave behind in motorsport will last a lifetime. Thank you for watching, and I'll see you on the next one.